Okay, good morning, chemistry students. I'm not sure when you're actually seeing this, but wanted to run through some answers here to the gas laws mixed practice worksheet that was assigned back on, I want to say it was Tuesday, April 28th. Um, so here we go. First thing, problem number one is a PV equals nRT problem. You write out your variables and you solve for what's missing. And so that one's not super scary. Only tricky part here is making sure that you understand that since we're talking about a problem that has a pressure in atmospheres, we want to use the 0.0821 liter atmospheres per mole Kelvin. We want to use that ideal gas constant because it has the right units of pressure. If it had been in kilopascals, we'd use the 8.31. And if the pressure had been in torr, which is the same as millimeters of mercury, we'd use 62.4. All right, let's scoot down here and give a look to number two. Same deal. We've got a temperature, a volume, and a pressure, and we want to find number of moles. So let me scoot that. So again, you've got ATMs. So we're going to focus on using the 0.0821, and that's just a little bit of math. All right, now I'm going to scoot this up a little bit here. Number three is an interesting one in that it asked you for molar mass, and you had to go back and remember what molar mass is. And the hint was given in the problem. Molar mass is the number of, grams per mole. And we can use PV equals nRT to figure out the number of moles. If you recognize that we only have one single set of data, we've got a volume, temperature, and a pressure. We use the right R value because it's in kilopascals. And so you figure out the number of moles. Now, once you figure out the number of moles, if you know the mass, and you remember that molar mass is grams per mole, you can get to that answer. So while we didn't explicitly go over that in the notes, or excuse me, in the class time video a couple days ago, my hope was that maybe that one we could have figured out. But there were definitely a couple that would have given you some difficulty, and I want to look at those right now. I think number 4 and 5, and this is totally my fault. Um, 4 and 5 would have been tricky. Now, number 4, Dalton's law of partial pressures is pretty easy when, let's say you have a container and it contains a couple of different gases. If you want to determine the pressure of the total pressure in that container, that total pressure is just the sum of the pressures of the gases in the container. So in a problem like number 4, you literally just add up the pressures to get the total pressure. Now, the reason that that's super important is because usually we can collect gases over a liquid, over a water. And so that's what's critical about understanding problem number 5. Let's imagine that I have a container filled with water, and I have an inverted container that is also filled with water, and some sort of reaction happens down here. And that reaction gives off a gas. The gas goes up, and the bubbles are trapped in this container. And so this little space right here, I'm kind of wiggling in with my pen, that would be where the gas is collected. Now, here's the tricky part. Water, even if it's not boiling, there's always some amount of water that's got enough energy to jump into the water vapor, into the gaseous state. And so what we have to do is we have to understand that the total pressure inside of this little space right here, that total pressure is actually made up of two gases. There's the pressure from the gas that we just collected, the gas of interest. And because we collected it over water, there's what we call a partial pressure due to water. And that partial pressure is going to be dependent on the temperature. And not surprisingly, as the temperature of the water goes up, the partial pressure of the water also goes up. And you would have to have a table of those values in order to do a problem like this, where it involves collecting a gas over water. So you can see that as the temperature of the water goes up, you can see that that pressure contributed by the water is also going up. Remember that torr is the same as millimeters of mercury, so we use those interchangeably. So let's go back, let's look at the problem here. And in number 5, it gives us some information, and we said that it was collected over water. So that's our key. So we're going to go ahead and we're going to copy that information over and make sense of this. So the first one said that it was collected over water and it had a pressure of 700 millimeters of mercury. So what that's telling you is that the actual pressure of the gas by itself is only 688 because 12 millimeters of mercury was contributed by the water vapor pressure. Now, once I then recognize what the pressure is of the gas, I go ahead and I use the volume, and I went ahead and converted this to liters just because, all right? Uh, this ends up being a P1 V1 N1 T1 P2 V2 N2 T2, a combined gas law problem. And in that one, as long as the units are on the left-hand side of the equation and the right-hand side match up, it doesn't have to be a certain unit. Whereas up here, for instance, if I had a volume that was in milliliters, because R is in liters, you have to use the correct units. If you're doing PV and RT, units are a little bit more of a crucial issue there. So this one says, look, we want to find the volume if it was collected at STP. So we go ahead and we look at the fact that we knew this information at the beginning, and we know that at STP, this is the pressure, this is the temperature, and we want to find the volume. So this is like those problems we were working a couple days ago, and then you can solve for the final volume. In part 5B, similar in terms of the setup. Only difference is I gave you different initial values. So you had a 581 millimeters of mercury initial pressure. You use the partial pressure of water at this particular temperature at 16 degrees. So you literally look up on the table that I showed you just a moment ago, and it says that the partial pressure at 16 degrees is 13.6 torr, 13.6 millimeters of mercury. We're going to still convert it to STP, and so that's how we get the answer there. All right, and I realize this may not answer every question that you have. That's why office hours are super helpful. Stop by and ask the questions that you have. Decided to omit number 6 simply because we're trying to do this virtually, and I just didn't want to dig too deep into the weeds on that one. Hopefully you can figure out number 7 and 8 simply because of molar mass. If you're at a certain temperature, you're going to have a certain amount of kinetic energy, and that means that the heavier things are going to be traveling lighter, they're going to be traveling slower, and the lighter things are going to be traveling faster. Problems 9 and 10 end up being good old-fashioned combined gas law problems, and hopefully just looking at those, you can make sense of that. So hopefully this video shares a little bit of knowledge with you, and that you guys have a wonderful day. See you soon. Bye-bye.